Hello viewers, welcome to the eMath learning platform by Peter Ekaja. I am now going to take you through probability theory, and this is A-level applied mathematics. Remember to subscribe to my YouTube channel, eMath learning platform, and in case of any questions or clarifications, my email and my contacts are clearly stated here below. So let's look at probability theory. Definition. Now, the probability of an event occurring is the measure of the likelihood that it will happen. That is how we can simply define probability. We can add something to that. Now, we need to all understand that probability is always given on a numerical scale of 0 to 1. What does this mean? It means probability only ranges from 0 to 1. Implying that we don't have negative values for probability and we don't have any value greater than 1 representing probability. Let's look at events. Definition. An event is a subset of a sample space. It is simply a subset of a sample space. Let's now look at types of events. We have quite many, as we shall see below. There are several types of events, namely, shall begin with independent events, mutually exclusive events, exhaustive events, and finally the undefined events. So we shall look at each of these at a go, and in today's tutorial we shall basically focus on independent events. So let's look at what we mean by independent events. Now, any two events, say A and B, are said to be independent if and only if the occurrence of one does not affect the occurrence of the other. So we are saying two events A and B are said to be independent if the occurrence of one of them does not affect the occurrence of the other. Let's add on to this. Now we are saying if A and B are independent, then probability of A intersection B is equals to probability of A times probability of B. This is one of the most important points. If two events A and B are independent, then their intersection, if you get the probability of their intersection, it is as good as getting the product of their probabilities. So in this case, we are multiplying the probability of A by the probability of B. Roman 2. Now remember, probability of A union B from set theory is as good as probability of A plus probability of B minus probability of A intersection B. But since probability of A intersection B is as good as probability of A times probability of B, then that is why you see us having probability of A multiplied by the probability of B instead of the intersection. So even the union changes slightly, but most importantly, Roman 1 defines Roman 2. That is what you need to understand. Now note that if A and B are independent events, then they are complements. That is to say, A complement and B complement are also independent. This is very interesting. What do we mean by this? We mean that if A complement and B complement are also independent, then the probability of their intersection is the same as the product of their probabilities. So probability of A complement intersection B complement is equals to probability of A complement times B times the probability of B complement. Let's look at some important laws that we need to follow as we proceed. The first law, which is very important, is that when you get a probability of A plus the probability of A complement, automatically you get 1. Now, this is not only restricted to this, it is restricted to any other probability. For example, if you have the probability of the union plus the probability of the complement of the union, you still get 1. A good daily example is if we say the probability of it raining is 0.5, then it means the probability of it not raining will automatically be 1 minus probability of it raining, which is 0.5. What does it mean? In this case, it means the probability of it raining on a given day plus the probability of it not raining should be equating to 1. So that is what we're trying to explain here. So do not restrict it only to this. We can expand it to other situations as we shall see ahead. Another Roman to another important law. This is specifically by De Morgan's. Now De Morgan's tells us that A complement, probability of A complement intersection B complement is as good as the probability of A union B but complement. This is something very important. Please note it clearly. This is by De Morgan's, a mathematician. So we call it one of the laws of De Morgan. And he has another one that if now we have the union of the complements, it is the same as the probability of A intersection B but complement. So you realize if you have the intersection, complement, you now have the union but complement. If you have the union of complements, we shall have the complement of the intersections. So that is how easily you can master the laws. We shall apply this as we proceed in the next questions, especially in the examples. So let's proceed to the next examples. Now, I want us to first try out and prove that indeed, if two events A and B are independent, it implies that the complements are also independent. Now, let's look at the proof for this. The first step is we should know that from De Morgan's rule, probability of A complement intersection B complement is as good as the probability of A union B but complement. But remember, when you get the probability of A union B complement plus the probability of A union B, they also equate to 1. So it means this is as good as 1 minus probability of A union B, as we can look at in the next step. Then on top of this, we can now think of probability of A union B. Remember we said probability of A union B is the same as probability of A plus probability of B minus the probability of A intersection B. So that is what we are going to simply substitute. But remember, the intersection becomes now this because we said A and B are already confirmed independent. So instead of saying probability of A intersection B, we shall have probability of A times probability of B. So from this step, we can simply open the brackets. So when you open these brackets, you realize we have 1 minus probability of A minus probability of B plus probability of A multiplied by the probability of B. But if you look at these two terms I'm pointing at, there is a common factor, which is probability of B. So we shall try to factorize it out. And that is exactly what we have done here. When you do so, you're going to realize that now we have a common factor again, which is 1 minus probability of A, 1 minus probability of A. And if you surely put it out, there is a silent one here, which will remain together with minus probability of B, also in its own bracket. And that gives us that. But remember, 1 minus probability of A into 1 minus probability of B can also be written as probability of A complement times probability of B complement, because we said probability of A plus the probability of its complement is equals to 1. So when you make probability of A complement the subject, it becomes this, and the same thing applies to this. So we have surely proved that if A and B are independent events, then even their complements are independent. Now I want to give you a simple trial also. You're also going to try out for me to prove that if events A and B are still independent, then Roman 1, A and B complement are also independent. Roman 2, A complement and B are also independent. Try out this, and in case of any challenge, you feel free to contact me for help. Let's move on to now the examples. Example number 1. Events A and B are such that probability of A equals to a third and probability of A intersection B equals to 1 out of 12. If A and B are independent events, they have defined them clearly as independent events. Find part A the probability of B and part B the probability of A union B. Let's look at the solution to this. So we're going to say, since A and B are independent events, what do we know about that? Probability of A intersection B is automatically the probability of A times the probability of B. So it means we can simply make the probability of B the subject. So it becomes probability of A divided by probability of intersection B divided by probability of A. And if you do so, you're going to divide 1 out of 12 by 1 out of 3. And if you press your calculator, you will surely come up with probability of B as 3 out of 12, which can be reduced to a quarter, as we can see. So that is our part A. Let's look at part B. Part B, they wanted probability of A union B. But what we know, probability of A union B is the same as probability of A plus probability of B minus probability of A intersection B. But remember, this is already defined in the question. So we shall simply substitute because we now know the probability of A and we know the probability of B. So when we come on to the next step, we are saying that probability of A intersection B is equals to probability of A multiplied by the probability of B for only independent events. So what are we going to do there? Simply substitute for probability of A intersection B as this. That is what I've done here in this step. Then the next step will be substitution automatically. So we knew the probability of A, we knew the probability of B as a quarter, then the product of the two. Then correctly press your calculator. It will give you a half as the probability of A union B. So that was our example number 1. Let's look at example number 2. They're saying events A and B are independent, such that probability of A union B is equals to 0.80 and probability of A is equal to 0.5. Find Roman 1 probability of B, Roman 2 probability of A complement intersection B. What do we do? Roman 3 probability of A complement union B, and I think we can now go to the solution. Roman 1, they want us to get the probability of B. But remember, we can begin from probability of A union B, which is given, and we define it as we said earlier. This is appearing in this form because the two events are independent. So it means we are simply going to substitute. So we have 0.8 for probability of A union B, 0.5 for probability of A. We don't know the probability of B, so we leave it as it is, but we still know the probability of A here. We also substitute it, and now we have this term and this term as like terms. Should you move this to the left-hand side, then simplify this, automatically you will be able to divide through by 0.5 now, and you get the probability of B as 3 out of 5 if you press your calculator. So that is simply going to be our solution for Roman 1. Let's look at Roman 2. They are saying we find probability of A complement intersection B. Now, since we are very sure that the two events A and B are independent, remember I gave you some trials, it also implies that the complement of A and B are also independent. And I gave you that proof. I hope you will prove it and indeed believe that it is true. So we are simply going to go with this shortcut. But remember, probability of A complement is as good as 1 minus probability of A. Then the probability of B, we already have it. So we shall simply do that mathematics. So we are trying to explain how to get probability of A complement, which is already this. And after that, we simply get 0.5. Then we go and substitute in our formula. We go and substitute in our formula. Remember, we had our probability of A complement intersection B as this. So should you substitute now the probability of A complement, which is 0.5, and substitute the probability of B, which is already 3 out of 5, we shall come up with the next step as this. And when you press your calculator, you will come up with 0.3. So let's now move on to Roman 3. Now, Roman 3, they wanted the probability of A complement union B. So, from what we know, the mere fact that they have placed a complement on A, we shall still define this the way we define probability of A union B. Only that wherever we have A, we shall put a complement. That is the simple logic. So because we know probability of A union B is equals to probability of A plus probability of B minus probability of A intersection B, since we just have a prime on a complement on A, we simply insert the complements wherever we have A. If it was also on B, we would simply still do the same on B. So that is the logic behind this. So we realize we already have this probability of A complement, we have the probability of B, and I think we also had this some time back. So let's look at the next step. It's a matter of substitution. So we substitute, press your calculator, and you'll come up with 0.8 as your required probability. Now, dear viewers, the learners, from this are two good examples we have illustrated for you. I now beg you to also try out the following questions. I tried quoting out the answers for you in the brackets, so you make sure as you try, you confirm with the answer I've quoted for you in the bracket. And like I've always said, in case of any challenge, feel free to consult because it is free. So that is question 1 and question 2. And finally, we shall move on to question 3, which is also given as this, together with its answers. And with all this, I think I have all reasons to thank you very much. May God bless you and have the best of your day. Only remember to share this with your friends out there. Remember to subscribe, encourage them to also subscribe and like my videos on YouTube. Our YouTube channel still remains eMath Learning Platform. Thank you.